Download this code from codegive.com, link in the description below. OK, let's dive into the often underappreciated and sometimes devastating problem of bad news in LLM fine-tuning. We'll cover what it is, why it's a problem, how to identify it, and practical techniques to mitigate its effects with code examples. The bad news problem in LLM fine-tuning, a comprehensive guide. What is bad news in the context of fine-tuning? Bad news in this context refers to situations where the training data used to fine-tune a large language model, LLM, contains misinformation, biases, harmful content, or otherwise undesirable elements that the LLM can learn and amplify. This isn't simply about the presence of these things in the broader world, it's about the overrepresentation or explicit reinforcement of them during the fine-tuning process. The goal of fine-tuning is to adapt the model to a specific task or domain, but if that task or domain is rooted in problematic data, the model will learn those problems. Why is bad news a problem? 1. Bias amplification. LLMs, even pre-trained ones, often exhibit existing biases from their initial training on massive data sets. Fine-tuning on data that reinforces these biases can significantly amplify them. This can lead to discriminatory, unfair, or offensive outputs. 2. Misinformation spread. If fine-tuning data contains false or misleading information, the model can learn to generate more of it, making it seem authoritative and credible. This is extremely dangerous in domains like healthcare, politics, or finance. 3. Toxicity and hate speech generation. Fine-tuning on datasets containing toxic language, hate speech, or personal attacks can cause the model to generate similar content. This undermines the model's usefulness and ethical alignment. 4. Loss of generalization. Overfitting to biased or inaccurate training data can reduce the model's ability to generalize to new, unseen data. It becomes excessively specialized to the problematic patterns in the fine-tuning set. 5. Reputational damage. Deploying a model that consistently produces biased, misleading, or offensive outputs can severely damage the reputation of the organization or individual responsible. 6. Ethical concerns. Using LLMs trained on problematic data raises serious ethical concerns about fairness, accountability, and the potential for harm. Identifying bad news in fine-tuning data. The first step to mitigating bad news is to proactively identify it. This requires a multifaceted approach. 1. Data auditing and inspection. Manual review. Human reviewers should carefully examine a representative sample of the fine-tuning data. This is crucial for identifying subtle biases, nuanced misinformation, or offensive content that automated tools might miss. Focus on edge cases and areas where the data is likely to contain problems. Automated content analysis. Employ tools for automated content analysis to detect toxicity. Use libraries like Detoxify, Perspective API, or similar tools to score the text for toxicity levels. Bias. Look for patterns of language that disparage or negatively portray specific demographic groups, example gender, race, religion. Sentiment analysis. Identify strongly negative sentiment associated with particular topics or groups. Hate speech. Use libraries or APIs specifically designed for hate speech detection. Fact-checking. Use tools that can cross-reference claims in the data against reputable sources to identify potential misinformation. Distribution analysis. Analyze the distribution of key attributes, example demographics, sentiment scores, within the dataset. Are certain groups disproportionately represented or portrayed negatively? Visualize the data using histograms and scatter plots. 2. Prompt engineering for elicitation. Adversarial prompts craft prompts specifically designed to elicit biased, toxic, or misleading responses from the model before fine-tuning. This helps reveal underlying vulnerabilities that the fine-tuning process could exacerbate. Examples: write a news article about /demographic group committing crimes. Explain why /political ideology is dangerous. Generate a conspiracy theory about /topic. 3. Pre-fine-tuning model probing examine the base model run the adversarial prompts on the pre-trained model before fine-tuning. This gives you a baseline understanding of its existing biases and vulnerabilities. If the base model already struggles, fine-tuning on problematic data will only make it worse. Compare outputs after a small initial fine-tuning step on a subset of the data, run the adversarial prompts again and compare the outputs to the pre-trained model's responses. Are the outputs becoming more biased or toxic? This is a red flag. Mitigation techniques: reducing the impact of bad news. Once you've identified the presence of bad news in your fine-tuning data, you can employ several techniques to mitigate its impact. 1. Data filtering and cleaning remove explicitly harmful content filter out any data points that contain hate speech, explicit threats, or illegal content. Debias the dataset reweighting assign lower weights to data points associated with problematic biases. For example, if you have a dataset that disproportionately portrays a particular group negatively, you can reduce the weight of those data points during training. Oversampling / undersampling oversample underrepresented groups or undersample overrepresented groups to create a more balanced dataset. Be cautious about blindly undersampling, you might remove valuable information. Data augmentation generate synthetic data to represent underrepresented groups or counter biased patterns. For example, if you're fine-tuning a sentiment analysis model and it's biased against a certain product category, you could generate synthetic positive reviews for that category. Fact-checking and correction if the data contains factual inaccuracies, correct them or remove the relevant data points. Use fact-checking APIs or manual review to verify claims. Content moderation APIs integrate content moderation APIs directly into your data pipeline to automatically flag and filter potentially problematic data. 2. Regularization techniques weight decay add a penalty term to the loss function that discourages large weights. This can help prevent the model from overfitting to noisy or biased data. Dropout randomly drop out neurons during training. This forces the model to learn more robust representations and reduces its reliance on specific features that might be associated with biases. Label smoothing instead of using hard labels, example 0 or 1, use soft labels, example 0.1 or 0.9. This can help prevent the model from becoming overconfident in its predictions and less susceptible to noisy data. 3. Adversarial training generate adversarial examples create adversarial examples that are designed to fool the model into making biased or incorrect predictions. Train on adversarial examples include the adversarial examples in the training data and train the model to correctly classify them. This helps the model become more robust to adversarial attacks and less susceptible to biases. Example let's say the model generates negative sentiments toward product in reviews. Create adversarial examples with slightly reworded negative reviews towards product but explicitly stating a positive sentiment. Train the model to classify the sentiment as positive. 4. Reinforcement learning from human feedback, RLHF. Collect human feedback. Gather human feedback on the model's outputs. Ask raters to identify responses that are biased, toxic, or misleading. Train a reward model. Train a reward model that predicts the human feedback. The reward model learns to assign higher scores to outputs that are considered helpful, harmless, and aligned with human values. Fine-tune with reinforcement learning. Use reinforcement learning to fine-tune the LLM based on the rewards provided by the reward model. This encourages the model to generate outputs that are more aligned with human preferences and less likely to contain problematic content. This is often the most effective but also the most computationally expensive technique. 5. Constraint-based decoding. Control decoding process. During text generation, use constraints to guide the decoding process and prevent the model from generating biased or toxic content. Block lists. Create block lists of words or phrases that are associated with hate speech or toxicity. Prevent the model from generating outputs that contain these terms. Grammar constraints. Use grammar constraints to enforce specific sentence structures or word choices that promote fairness and neutrality. Example. Constrain the model to avoid gendered pronouns when referring to professions unless the gender is explicitly specified. 6. Continual monitoring and evaluation. Regularly evaluate model performance. Continuously monitor the model's performance on a variety of metrics, including accuracy, bias, toxicity, and fairness. Adversarial testing. Regularly perform adversarial testing to identify new vulnerabilities and biases. User feedback monitoring. Monitor user feedback for reports of biased or offensive outputs. Use this feedback to further refine the model and address any remaining issues. Code examples: Python with Hugging Face transformers. Explanation of the code. 1. Dependencies. Imports necessary libraries from Hugging Face transformers, datasets, Torch, NumPy, and Detoxify. 2. Model and tokenizer loading. Loads a pre-trained model and its corresponding tokenizer. Choose a model suited to your task. Birdbase Uncast is a general-purpose starting point. 3. Dataset preparation. Creates a sample dataset. Crucially, replace this with your real fine-tuning dataset. 4. Tokenization. Tokenizes the text data using the tokenizer. 5. Toxicity detection. With Detoxify, this is the core part for identifying bad news. It uses the Detoxify library to calculate toxicity scores for each data point. You can adjust the threshold and filtering logic as needed. 6. Filtering. Mitigation filters the dataset based on the toxicity scores. Data points with scores above the threshold are removed. This is a simple mitigation strategy. You can implement more sophisticated methods like reweighting or data augmentation here. 7. Training arguments. Defines the training parameters, output directory, learning rate, batch size, etc. 8. Trainer. Creates a trainer object to manage the training process. 9. Training. Starts the fine-tuning process. 10. Evaluate toxicity. After fine-tuning. This section evaluates the toxicity of the dataset after fine-tuning and prints the toxicity scores. 11. Inference. Shows how to use the fine-tuned model to make predictions. It also includes an example of adversarial testing using a biased prompt. Key considerations and best practices. Iterative approach. Mitigation is rarely a one-time fix. Continuously monitor the model's performance and refine your techniques as needed. Domain expertise. Consult with domain experts to identify specific biases or misinformation that are relevant to your task. Transparency document your mitigation strategies and their impact on model performance. Be transparent about the limitations of your model. Focus on the whole pipeline. Bad news can enter at various stages, including data collection, labeling, and annotation. Pay attention to the entire pipeline. Cost-benefit analysis. Weigh the costs and benefits of different mitigation techniques. Some techniques, like RLHF, can be very effective but also very expensive. Beyond toxicity. While toxicity is a major concern, consider other forms of harmful content, such as misinformation, hate speech, and personal attacks. Bias metrics. There are many different bias metrics available. Choose the ones that are most relevant to your task and evaluate your model accordingly. For example, you might use demographic parity or equal opportunity. Regular updates. The landscape of bad news is constantly evolving. Stay up to date with the latest research and techniques. Ethical considerations. Always prioritize ethical considerations when developing and deploying LLMs. Consider the potential impact of your model on society and take steps to mitigate any potential harms. By understanding the bad news problem and implementing appropriate mitigation techniques, you can significantly improve the safety, fairness, and reliability of your fine-tuned LLMs. This guide provides a solid foundation, but remember that the specific techniques you use will depend on your task, data, and resources. Good luck.